Hi everybody, welcome back. So we have a working power supply now, and what I'm going to do is I'm going to show this to you, and in this video I'm going to go over and answer some of the questions and some of the comments that you left in the previous video, because I got quite a few comments and some of them are very good, and I want to address them and talk about them, and maybe we can learn some things together. How about that? All right, let's check it out. Okay, first things first, I have the power supply assembled. I'll go over what all I did on here later on in the video, but we're just going to check just the plus and minus 90 volt supplies, or 90 something volts as it is. And what I have is I have two traffic signal bulbs on here, and they're rated at 130 volts at 116 watts each. And they're not going to, obviously, we're only going to put about 100 volts on, or just under 100. We're going to put 90 something volts on them, so they're not going to run at full power. But what this does with the transformer losses, with all of the things, you know, the diodes, all that, the bulbs themselves, the wiring, looking at my meter over here, when I have no current limiting on it and just connected to the mains, this whole setup with these bulbs is going to draw somewhere around 240 to 250 watts. And one of the things I wanted to check is to make sure that the transformer buzz wasn't too bad, and it's really not. Remember, when you're up to that volume, you know, in your speakers, where it will be drawing that much power, a little bit of hum inside the case of the stereo is not going to be audible at all. You'll find out that when it's under very low load, it's dead silent. There's no hum or no buzz on the transformer at all. We'll get a little bit into shielding and things like that later on in the video, but let's just look at the voltages right now. So turning this thing on, I'm using the current limiting bulb first. So we're not going to put a full 120 volts into this. We're going to have somewhere around about 100 volts going into here. So let's turn this on. Yeah, we have about 100, what do we have? Yeah, 102 volts. So there's 102 volts going into the mains. You can see these bulbs are pretty bright. And you can see my plus and minus power supply is plus and minus 71.6. And that's because these bulbs are limiting the current and limiting the voltage going in there. And by the way, this is wired up, and it's powering this board, so this board is powered right now. You can see the capacitors that are relevant to what we're doing I have replaced. The ones for the scope, the high voltage ones, I've not done anything with. You can see I even have the fuses out. Okay, so if I turn this on to direct power, you can see it gets a lot brighter. You can't hear anything from the microphone. If I put the mic right up to the transformer, I'll do that for you. But you can see we're looking at about 94 volts. And that's higher than, that's more like what you would see on the 2600. It's going to be somewhere in that range, in the 90 range. And so since this is a 2500, we're going to be putting a little bit higher voltage on it. We'll get into that later too. I'll talk about it. So it looks really good. Everything looks good. And here's the transformer buzz with current being drawn. I don't know if you heard that or not, but I can hear it a little bit. But you're never going to hear that. So let me put it back on limit so these bulbs dim down a little bit. And then let's shut off the power. And you can see that cap bank actually has some pretty good storage for what it is. All right, so let's get into some of the details. So the first thing I want to talk about, because it is a change that I had to make because of this transformer and the way we're setting it up with single rail supplies instead of having two separate right and left channel power supplies, is looking, let me see if I can find a pointer here somewhere. There we go, we get a chopstick. So looking at these resistors, if you notice, the first one is where it's supposed to be on this. This is a capacitor upgrade board you can buy online. I think it's on eBay, you can find it. And these are the bleeder resistors. They were originally 4.7K, little, in the original amplifier power supply. And normally these would go from the plus to the ground of, or I'm sorry, from the minus, from the negative supply to ground. And the positive supply did not have any bleeders on them. That's just the way it was. Let me see, I have a schematic here, I'll show you. It's a really odd thing. But if you look, here's the power supply. And if you look in here, right there's those bleeder resistors, 4.7K. And if you notice, they're bleeding down the positive supply on both of them, but not the negative. Okay. So what I did was I moved the leg on this one from here to the positive terminal over here. So now it bleeds down both the positive and negative supply equally. That's one change that I made on that board. So it'll bleed both sides down. What was happening was, before I realized that, one side would bleed down nicely, the other side would just sit there and stay charged up forever. And I'm like, why is it doing that? That's why. Got a bazillion different comments on how to mount this second little transformer on top. And I also heard a lot of concerns that you folks had. But let's just start with how I mounted this. I used a 5/16 bolt. This is a 6-inch one. If you buy a 5/16 by 5.5 inch, it's the exact, you don't have to cut it down. It's the perfect length. Now what I did was I drilled a hole in this plate down here. Let's see, zoom out a little bit. Drilled a hole in the plate in the middle, pushed this up through, and I used a big fender washer, like big diameter fender washer on both sides, and bolted this to here like that. Then I put the big transformer over top, and I put a stopper bolt, a stopper nut underneath there. So I can't over tighten this and put too much strain on the, on the windings. It's tight enough that it'll never move, but I won't over tighten it. So that way I could crank down on the bolt on top of this plate here. And this plate has like a rubber gasket underneath it. So I bolted that down, and then when I put this top on, I had to open the hole for this one up a little bit for 5/16. And then when I tighten this, it will tighten against the bolt underneath here. So I'm not pushing the whole thing down and crushing this bottom transformer, if that makes sense. So now it's very rugged. It's not going to go anywhere. It's very tight, and that mounted up really well. Now some of you were very concerned that this is metal and this is a transformer. Let's talk about how a toroidal transformer works. In a toroidal transformer, all of the magnetic field is contained within the core around this way. In other words, it's not like, since the windings are going around like a donut, like going around the core, your magnetic field is going to be contained within those coils. Whereas on an EI transformer, or what they call an open core transformer, let me get one here. These ones, you have a core going through the middle and then this going around. It's going to have a very different magnetic signature than one of these. So the bottom line is the magnetic field is pretty much neutral inside the middle of the toroid. So putting a metal rod in there isn't going to do anything. What will do it is if I took a jumper, let me show you with a jumper, and I made this right here, I touched this bolt that's going through the middle of the core to ground. What that does is that makes one complete turn around the coil, just like this, right around the core. That is called a shorted turn. That will fry the primary of this transformer in pretty short order. So you never want to make a shorted turn. So in other words, it's okay for this to be bolted on the top and the bottom. You do not want it to be wrapped around though. You don't want it any metal or any conduction between here and here electrically. because as soon as you do that, you just made a shorted turn. Does that make sense? Now, a toroidal transformer can have some slight magnetic coupling to things, but it's typically so small that it's negligible. You don't worry about it. And you really don't have a lot of E-field coupling, you know, like a lot of electrostatic, although you can. So shielding depends upon what kind of field you're trying to suppress. So if you're trying to suppress the H field or a magnetic field of the transformer, putting a piece of copper tape around here and you know, grounding it isn't going to do a thing. It'll go right through that. However, if you're trying to keep this transformer from capacitively coupling from something, then if you put a copper shield around there and you grounded it, that would help suppress that capacitive coupling. So again, the strategy you're going to use for shielding is going to depend on, number one, the transformer type, and number two, which field you're trying to suppress. Bottom line is, I'm not going to do anything to this transformer until I install it and try it. Now, if I pick up some hum in the phono stage or in the tuner stage, then we'll try to determine where it's coming from. Is it, you know, is it electrostatic, like a capacitive coupling, or what is it? And then we'll deal with it at that point in time. But I have a feeling that I'm not going to have to even worry about it. Okay, you can also see down here, we just have a single bridge rectifier now. Again, this is a single power supply driving both the left and right channels, instead of having two separate power supplies. In other words, the other transformer had two separate windings on it. One set of windings for the left channel, one set of windings for the right channel. This just has one big set of windings for both channels. So you only need one bridge. This is not the same kind of, the little dinky ones they used on the original really are not high current, and they're not high surge current either. They're adequate for what they were doing, but I would not use them for this. So what I used, because I had in stock, is right here. So this is a 600 volt bridge rectifier. It can do up to 40 amps maximum, and it can do continuous 20 amps, like all day long, no problem, of current, forward current. The maximum forward surge current is 300 amps on this. I wrote it down, I looked it up. So this thing can handle a 300 amp surge. Now, I think we may even be exceeding that for a split second when it goes to charge the capacitors up initially. So you're still going to need a soft start circuit, and even if it could handle that, that's going to be so hard on your incoming line that you could pop your circuit breaker in the house. So we're still going to put a soft start circuit in there. So we're really kind of upgrading the power supply. Now, this thing, because I probably could have taken 2 more turns off and lowered that voltage even further a little bit, and it would have been almost right on, what we need. But as it is, it's a little bit higher. This is closer to the voltage that you would see on the 2600. The other thing is the 2600 had the same capacitance for the main filter caps here, but they were rated at 105 volts instead of 100 volts. They needed to do that because they were getting very close to 100 volts on there, as we are with this too. We're up there pretty close. But believe it or not, a capacitor rated at 100 volts, if it's running at 98 volts, it doesn't really change the lifespan of the capacitor at all. It's more concerned about temperature and it's more concerned about not exceeding that maximum voltage. So as long as you keep it under its rated voltage, you're good. The bigger deal is you don't want it to run at high temperatures, even though these are 105 degree caps, and I think the original ones were 85 C. So this should be a pretty robust power supply. I think we're going to get a little bit of sag on it, like what this was showing us here, and that's what we want, because that'll keep that voltage down, a little bit further. Now, this just has two 30-volt windings, and I have them connected in series, and the place where the two windings connect together, that becomes the center tap, and that goes to ground here. And we're using a star grounding system. So you see where all these lugs are all the grounds that are going to go out to the receiver are all going to that star ground. If you remember, the first 2500 I did had a few hum issues with it, and it turned out to be the grounding was not as good as it could have been. So we straightened that out, and it made a huge difference. So I've kind of learned from that one. So anyway, that's good there. So let's turn it on again, and let's look at what our voltages are here. Okay, I have this turned on, and I do have current limiting, but I don't have a whole lot of current limiting, because now there's 108 volts instead of 125 or 121 volts going in. So it's not going to really affect this very much, because this is a regulated supply. So looking here, we should have like a 12, or I think it's like 14.1 or something, but there's 14.2, then here's your plus and minus 31 volts, there's minus 32, plus 32, there's the ground, and then the other 14, that's on either side. And I believe that is an adjustable power supply, which means I should be able to, if I can find an adjuster, there we go. So I hit this, get on here, and nope, that doesn't do anything. Yeah, that's the 30-volt supply, so we can get that down to like 31 there. And there's your 31, plus and minus. They're off a wee little bit, but that's no big deal. Even in the schematic, it shows them being off by about a half a volt between them. And then this is your 14 volts, and if you look here, they're calling that 13.5 volts right there. So it's a little bit high. It's 14. But again, that's not a huge problem either. And that might just be one of the Zener diodes or something, and the regulator is off a little bit. So that's okay. We could change that or just ignore it, because I don't think it'll make that big a difference. So if you really want to know the main difference between the Marantz 2500 and the Marantz 2600, it's not much. So you have the bigger power supply, and when I say bigger, it's about 5 volts higher. Between 5 and 7 volts higher, I think, than the 2500. In addition, all of these transistors, like up here, and all of these ones, they're all the same. They didn't change anything there. The only changes they made was in here. They changed a couple values of the resistors here in order to kind of change how much swing this thing will have to give it the extra amplification, the voltage that it's going to need to get to that 300 watts instead of 250 watts. If they didn't do that, and they did what we did here, you'd have probably would help the distortion and everything a little bit on the amp, but you really wouldn't get a whole lot more power. You have to change some things in the voltage amplification stage, and I think I said that in the last video. So like for instance, this, what is this? This is a 4.3K resistor here, and I think on the 2600 they lowered it to like a 2.7K or something like that. Did the same thing with this resistor. They changed it. A couple of the ones over here on this end got changed as well, and that was just enough to give you the extra gain you needed. They just tweaked it a wee little bit. It's the same circuit. They just changed the couple of resistor values. Other than that, there's not much difference that I could find. Again, I'm not an expert on these because I've only worked on a couple of them, but looking at the schematics, I was surprised that they really did not reinvent the wheel when they came out with the 2600 versus the 2500. And I've heard debates over which transformer was more reliable, the newer one or the on the 2600 or the older one on a 2500. I would think the 2600 would be less reliable because it's the same size transformer with you're drawing more power through it, I guess, and you have higher voltages on the windings. So I don't know. Another thing that confused a lot of people was when I removed a couple of turns from this. Let's see if we can look at the actual schematic here of the transformer. Okay, and I'm not getting fancy on this. I'm just going to kind of do this on the camera here live. And if you look, you have two windings here. This is the one with the 175 or 78 volt winding, whatever you want to call it. And this was the other one. They are separate. There is no center tap. I think some people were asking me about center taps and did I mess up is one side going to be different voltage than the other? No. Two things. Number one, these two coils are bifilar wound. What does that mean? That means they took two pieces of wire instead of one, and they wrapped them both around together like this. So this would be cut. So basically you had two secondaries wound together side by side. So they're the exact same length of wire. They're covering the same spot on the core and everything, but they are not electrically connected. So when I grab those two blue wires, so on this, looking here, you have the blue wires and the green wires. And there's two blues and two greens. The blue wires, as you see, represent one end of each of the coils. See, there's a blue wire here and a blue wire here. The green wires represent the other end of the winding. So what I did was these two blue wires, this one and this one, were right next to one another on that core. So when all I did was I unwound this side from both of them equally. Now, that would make both of these the same voltage and the same physical length. Then what I did was I took the blue wire on this side and the green wire on this side and tied them together and ran those to ground. So this becomes your center tap here where these join together. So now you have a 180 volt or 190 volt center tapped secondary. And that's how you're getting your plus and minus 90 something volts like that. Does that make more sense? Okay. Now, does removing a couple of coils reduce the power of the transformer? Well, that's not really how transformers work. Transformers are dependent upon the load that you're connecting to them. And the thing is, if the voltage is too high and you put a load impedance that is too low, it's going to cause the transformer to draw excessive current. That's going to put extra heat on the windings and cause them to be damaged. Conversely, if you have too high of an impedance and too low of a voltage, the transformer is going to deliver less current to that load and deliver less power. So really, it's not about how many turns of wire you have. It's about what load you're putting on those windings. The other thing is if you're going to put a real heavy load on a secondary, whatever it turns out to be, you have to make sure the diameter of the wire that's used to wind that can handle that type of current. Now, that's pretty thick wire they used on this. This is like number 16, I think, 16 gauge, and I don't know in millimeters what that is. But that easily can handle like 10 amps or so. And so therefore, as long as we don't continuously draw more than 10 amps across this whole thing, you're going to be okay. And you're not going to go anywhere near that on this. You could see when I had 250 watt or 240 watt load on this, the input of the thing was only drawing 2 amps. So it really isn't that much. So, and it all has to do with the flux density of the transformer, you know, what kind of core material, its cross-sectional area, the length of the wire, the thickness of the wire, how many volts per turn you're applying to the wire. All those things come into play there. So long story short, what I did is good. It will not hurt anything, and it will work just fine. If anything, I didn't take enough turns off of this. I probably should have taken 1 or 2 more turns off of each side. That would have lowered these 2 more volts, and that would have made a huge difference. But I think we're going to be okay. We're not going to exceed anything, because this now is more like a 2600 power supply instead of a 2500 power supply. It'll work. So you can see I still have that 12 volt and that 18 volt winding, these two here, the browns and the oranges. And right now we don't need those, but moving forward, when we get to the scope part of this, that's going to be way down the line. We are going to be using at least one, if not both of these, to address that issue. But for now, just to run the receiver without the scope, we do not need these. They're just blank. We'll just cap them off for the moment. I think we're ready to install this in the receiver and see if it'll power up. Now we're going to have to do a few tests on the amplifier modules first, which I will do that before we get too deep into it. But that'll be the next video. I just wanted to get this one out there to kind of show you the power supply and address a few of the questions that I had. So I hope I did. And again, we'll see you shortly. And I wish you all peace, joy, happiness, and good health in your lives. And we'll see you again very soon. Take care, everybody. Bye-bye.